Okay, so welcome back. This is our fourth video about map and MP inference. And we have been discussing ways of using systematic search for map queries. And we must rely into an upper bound in order to prune the search and make it more feasible. We haven't discussed one way of computing those upper bounds, but now we're going to see a different way based on node splitting. And this figure here is going to illustrate the idea of node splitting. Basically, we are taking some nodes and split them as we did here with the S node and also with the T1 node. When we split nodes, what we are doing, we are reducing the tree width of the network because we are eliminating loops, right? So we know that the tree width of a network can increase because of two main factors. The first one is the number of parents that we have for a node, and this factor we cannot change using node splitting. But the second one is the presence of loops, and we can eliminate loops by splitting nodes. One interesting characteristic of this technique is that we can generate what we call a spectrum of upper bounds. And it means that the more nodes we split, the more loops we can eliminate. So we can reduce the tree width, make the inference faster, but also we're going to generate less tight upper bounds. So we need to decide which nodes are going to split and how many nodes are going to split very carefully in order to have a good trade between performance and the tightness of the upper bound. So the technique involves first identifying a loop like we have here, and choose one edge, for instance the ST2 edge here, and cloning the parent variable. So I'm going to clone S and create a new variable that we'll call S hat. So we have here in this figure. And we need to decide what's going to be the parameters for S hat and also how we're going to deal with T2, because T2 used to have S as its parent, but now we're going to have S hat as its parent. And the technique is very simple. First, what we're going to do is to associate uniform CPTs to the hat variable. So in this case here, S hat will have a uniform CPT. Basically, S has just two variables, just two values, that's male and female. So I'm going to associate 0.5 for male and 0.5 for female, and that is going to be our distribution for the S hat variable. And for T2, you're going to be even simpler. We're going to just replace S by S hat in T2 CPT. And we're going to compute now what's going to be the MPE for this new network. So one key observation here is that these transformations, we are doing that to reduce the tree width of the network. So it's very important to do that. So we are not splitting any nodes or the nodes that we want. We're going to have to select the nodes in order to reduce the tree width. As I mentioned before, we are looking for loops because we know that loops can increase the tree width as well as the number of parents that we have for a node. But for the number of parents, we cannot change that. So we can change the loops. So I'm going to identify the loops and I'm going to open those loops as we are doing here with S and also as we are doing here with T1 and A. So the idea is that if we reduce the tree width, it's going to be cheaper to compute the MPE using variable elimination. So we're going to change the network from the original network to what we call a splitted network, like this one here, where it's feasible to compute the MPV. But as you may suspect, the probabilities that we compute with an MPE query in this splitted network will not be the same as the MPE probability that we compute in the original network. But we can show that they will be an upper bound. So we can use those upper bounds, those probabilities, to speed up the search that we do with our procedure of systematic search. Okay, so this is the central equation here that states that this MPE in the splitted network is an upper bound for the MP in the original network. So just to explain the notation here, what we are calling E and the E hat is going to be the evidence, and also the evidence instantiated to the splitted variables. So for instance, if we have evidence that is S equal male and A equal true, this E hat will be this evidence applied to the split networks. And in this case, as we are splitting S variable and also T1, but we are not splitting A, in this case we only take S hat equal male, right? So we're going to apply this evidence also to this S hat variable. And this beta here is the total number of instantiations that we have in the cloned variables. So for instance, if we only clone the variable S, as S has only two values, so beta will be equal to. If we clone S and T1 as we did here, because S has two values and T1 has two values, beta is going to be 4, because there are 4 possible combinations of values for these two variables. And the idea is that we split the network and we use variable elimination to compute the MPE for this network. But it's important that this network will have a low tree width by design. So what it means that we're going to apply a procedure to reduce the tree width of this network. And usually what we do is to locate loops, and we split and we open the loops by splitting variables. And that way you're going to reduce the tree width, and you're going to be able to compute the MPE probability using the MPEV algorithm that we discussed before. So a central question is why this MPE in the splitted network is going to be an upper bound for the MPE in the original network. So in order to understand that, I think that the best way to go is to use a very simple example and see what happens when you split a very simple network. So we have this network here. Basically, it's only two nodes, A and B, and we have the probability of A here, the probability of B given A. So these are the parameters for this very small Bayesian network. But I also computed the probability of B and A. That's going to be the result of the inference if we join those nodes. So we have this joint probability here. So now we're going to split this network. And what we do is to select the edge that we're going to split. We only split the parent node, so we're going to split it here. We created this new node that's going to be A hat, and we have the A original node, and we have the B node. We need to decide what we're going to do with the parameters, right? And the technique says the following. For the A hat, we'll have a uniform distribution. So basically, we look at here where we have A has just two values, so A hat will have the same two values, and it will have uniform distribution, so 0.5 and 0.5. For the B variable, the only thing that we need to do is to replace the parent that used to be A, now is going to be A hat. So we have this table here originally for the B, the probability of B given A. Now we're going to have the probability of B given A hat. And I just replace here A by A hat. The probabilities are the same, 0.1, 0.9, 0.7, and 0.3. Now, let's compute the joint probability between A hat, and B. So in order to do that, we can forget about this guy here, because we don't have probability of B given A anymore. We only have the probability of B given A hat. So we're not looking at the table, we're going to look at these three tables here. That is A hat, the probability of A hat, the probability of B given A hat, and the probability of A. We have this entry here. So what we have to do, we have to look at the matching entries. So we have A hat, and B. So we have A in this row here, we have A hat in this row here, and we have A hat and B in this row. So we multiply and we put the result here, right? And we continue doing that. So for instance, for this entry here, we're going to have A hat, and not B. So I'm going to have A again here, A hat again here, and A hat and not B here. So we multiply those numbers together and put this entry here. So we continue filling in this table, but when you look at the numbers, we're going to see there is a pattern here. And the pattern, compare this table that has the joint marginal A and B and this joint marginal here between A and hat and B. What we can see is that for the matching assignments here, the values that we have here are half of the values that we have here. So look at this guy here, it's 0.2, and we have this 0.02, and we have this 0.01 here. We have this 0.18, and we have this 0.09. And see how they match, because we have A and B here. So we have A here and B here, and we also have A here and not B here, exactly as we have it there. And here we have not A and B, 0.56, and here we have not A and B with 0.28. And here we have not A and not B, and here we have not A and not B, also half of the value that we have originally in the joint marginal of A and B. These half values are coming from the fact that we have this uniform distribution here. So when we introduce this variable A hat, we multiply one more value, and this value is 0.5, so I'm going to halve the values of the probabilities that we had originally. Okay, that makes sense. And also we have these values here. They are a little bit like nonsense values, because here, if we see, we do not have a match between A and A hat. So we have true for A and false for A hat, true for A, false for A hat, false for A and true for A hat, and false for A and true for A hat. These values are a little bit nonsense, because we know, and of course the algorithm doesn't know it, but we know that A and A hat are supposed to be the same variable, so they should not have different values. But there is nothing wrong here. We can compare to those values. We just take the compatible assignments into the tables and multiply them together. You get those values. So let's take a look at the next slide. Okay, so now what I'm going to do is to multiply this probability here of A hat, and B by a constant beta. And beta is basically the number of possible values that the splitted variables have. So in this case, we have only one splitted variable, that is A. And the A has two possible outcomes that are going to be true or false, so beta is going to be equal to. And when I multiply this probability by beta, what I'm doing is nullifying the fact that we had before of multiplying the probabilities by half. So I'm going to return the probabilities into the values that I had originally. So we see that now we have this 0.02 is equal to this guy here. This 0.18 is equal to this guy here. This 0.56 is this guy, and this 0.24 is this guy here. And we also have these probabilities that were multiplied by 2, right? Those ones that A and A hat do not match. Now, let's suppose that we compute the MPE. So we're going to eliminate the variable A hat by doing the process of maximizing out the variable. So what's going to happen is very simple. Sometimes these values here are larger than the values that we have in the other rows. So in this case, we're going to take a larger value, substitute by the true probabilities, and we have this upper bound. Sometimes those values will be smaller than the values that we have in the original probabilities. So in this case, we're going to take the original probabilities, and our upper bound is going to be exactly the same probability that we had before. In both cases, as we are eliminating A, doing this maximization process, what we're going to have as a result is a probability that is larger or equal to the original probabilities. So just to think about one case here, let's suppose that we take this entry. So we are maximizing out this variable here. So we take another entry that matches this entry. That's going to be this one here. So you're going to maximize out this variable, and we're going to take the maximum between 0.02 and 0.14. So the result here is going to be 0.14, actually larger than this value here. For this entry here, we have A and not B. We're going to take this entry here that has A and not B too, and going to maximize. So it's going to be the maximum between 0.18 and 0.06, and now I keep the 0.18. That is exactly this value here. So at the end, as we eliminated the variables of both of those tables, we're going to get as a final result an upper bound for the original probabilities, and we can use that upper bound to prune the search that we do with the systematic search procedure. So here are some numerical results just to illustrate the idea. I will not show all the details here. We have this piece of evidence here that is S equal male and A equal yes. So the evidence for the cloned variables, because we are cloning the variables S and T1, is going to be just S hat equal male. So if we compute the MPE for this query in the original network, we get this number here. If we compute the MPE in the cloned network using this evidence here, E and E hat, I'm going to have this probability here, but we have this beta value, and in this case, it's going to be 4. Where this beta came from the fact that we have two variables, each one has two values, so in total we have 2 times 2, 4 possible combinations of the values for these two variables. So what we do, we compare now the original value of the MPE and check to see if it's going to be smaller or equal to 4 times 0.0836. And in fact, 4 times 0.0836 is 0.3344. So in this case, the upper bound is exact. Let's take a look at another example. So here we have only one piece of evidence. It's going to be A equal yes. So as A was not cloned, so this E hat is going to be an empty set. In this case, the MPE probability is this guy here. The MPE that we got in the cloned network is this guy here, and beta is equal 4. So beta is still 4 because we still have two cloned variables that are S and T, right? So now we have this probability here that must be smaller or equal to beta, that's 4 times what we got for the MPE query into the cloned network. And 4 times 0.099275 is equal to 0.3971, so actually its value is greater than the original value that we have for the MPE in the original network. So we can compare the complexity of the algorithms for computing the MPE queries that we haven't seen so far. So the algorithm that is based on a variable elimination, the MPE-VE, has the same complexity as the original variable elimination algorithm. So the complexity will be n times the exponential in W, where n is the number of variables that we have in the network, and W is the width of the elimination order. For the branch and bound technique, if we analyze with this idea of using node splitting to compute the upper bounds, what we do is that we start with any variable, so here should be n and not m, and we split the network, so we're going to introduce new variables that they are calling here the m new variables. So we're going to have a larger network that has the n original variables plus some other m splitted variables. But we expected to have a new elimination order, and this elimination order should have a smaller width that we are calling the W prime, right? So it should be W prime, should be smaller than W, so we expected that, right? Because we are eliminating the loops. So the complexity of inference in the split network is going to be this number here, right? So it's basically the same thing that we have here because we are using the MPE-VE to make inference in this split network, but now we have more variables. So we have n plus m variables, but we expect to have one smaller width, that is w prime. And things become a little bit daunting when we look at the size of the search tree, because the search tree will have an exponential size in n. And for each node that we have in the search tree, we have to compute this upper bound. So it's not going to be an upper bound that we compute just once. We, at different nodes, we'll have different partial instantiations, and we need to compute new upper bounds for those partial instantiations. So the total complexity of the branch and bound is going to be this guy here. We're going to multiply this one by this one here, so we're summing the exponents here, it's going to be n plus w prime. And it looks very daunting. But the idea is that this analysis is a worst case analysis. We expect that the pruning technique will eliminate most of the nodes in the search tree, so this n is going to be much smaller, and the w prime we expect to be much smaller as well, because when we split the network, we eliminated the loops. So it doesn't look very good for the branch and bound, but we expect the pruning will improve things, as well as the w prime is going to be much smaller than w. And we should remind that for the variable elimination, the time complexity is the worst and the best case at the same time, but for the branch and bound, it's the worst case, and we expect to improve the average case with the pruning. So that's good for this video. We're going to continue in the next one discussing the map queries. See you soon.